Hi everyone. In this video, we're going to find local extrema using first derivative tests. Here are the steps to find local extrema using first derivative tests. Consider a function f that is continuous over an interval I. Step 1. Find all critical points of the function f. Step 2. Divide the interval I into smaller intervals, using the critical points as endpoints. Step 3. Find f prime, or the derivative of the function. Step 4. Choose an arbitrary test point x in each of the sub-intervals of step 2 and evaluate f prime on those test points. If f prime is continuous over a given sub-interval, which is typically the case, then the sign of f prime in that sub-interval does not change, and therefore can be determined by choosing an arbitrary test point x in that sub-interval. The respective sign of f prime on a particular test point represents the sign of derivative in that particular sub-interval. Step 5. Use first derivative tests to determine whether the function f has a local maximum, a local minimum, or neither at each of the critical points. Let's see this example. Use the first derivative test to find the location of all local extrema for the function f of x equals x cubed minus 3x squared minus 9x minus 1. For our solution, let us do step 1, and that is to find all critical points of the function f. The first step is to find the derivative. So f prime of x is equal to 3x squared minus 6x minus 9. And from here, let us set f prime of x into 0. So we will change the left side into 0. So we have now 0 equals all the members of the right side. Then let us solve for x. Observe that the right side has a common factor, and that is the number 3. If we factor out that number 3, we will have 3 times the quantity x squared minus 2x minus 3. Let us simplify further by dividing this equation by 3. So the equation now becomes 0 equals x squared minus 2x minus 3. Then let us solve for x. We can solve this equation by factoring. So the factors are x minus 3 times x plus 1. And from here, let us equate each factor into 0. So the x minus 3 equals 0 and the x plus 1 equals 0. Solving for x in the first equation here, we transpose the negative 3 to the right. So x is equal to positive 3. And on the other equation, x plus 1 equals 0, the x value here now becomes negative 1. We can see here that we have two critical points when x is equal to 3 and x is equal to negative 1. Let us copy these critical points under step 1, just like we have here. Step 2 is to divide the interval I into smaller intervals using the critical points as endpoints. We are able to find the critical points. Now, let us plot them in the number line. Here is our number line. We write here -1, and on the right is the +3. We can see that our number line here is divided into 3 sub-intervals. The first interval is here, and we name this as from -∞ to -1. Next interval is from -1 to +3. And the other interval here is from +3 up to +∞. Step 3 is to find the derivative. A while ago, we are able to find the derivative from step 1. So that is f prime of x equals 3x squared minus 6x minus 9. Step 4, choose an arbitrary test point x in each of the sub-intervals of step 2 and evaluate f prime on those test points. We have 3 sub-intervals here. Let us choose arbitrary test point on each of the sub-interval. On the interval here, we can choose a -2, which is the first integer on the left side of -1. On the interval from -1 to +3, we know that 0 is part of this interval, so we can choose the number 0. On the third interval, we can choose the number 4. That is the first integer after number 3. Now, let us evaluate the f prime or the derivative on those test points. Let's start with this -2. So we have f prime of -2 is equal to 3 times the square of -2 minus 6 times -2 minus 9. The square of -2 is +4. 4 by 3 is equal to 12. -6 times -2 is +12. Then we copy the -9. When we simplify these numbers, the final answer is +15. We are more concerned on the sign of the number 15. So this positive represents the sign of the derivative on this interval. So we take a note here that we have a positive or the plus sign, and we know that we have an increasing function on this interval. Next is the f prime of 0. This is equal to 3 times 0 squared minus 6 times 0 minus 9. We can simplify this into -9. We are more concerned here about the sign of the 9. So this is negative. The negative sign represents the sign of the derivative in the whole sub-interval here. Let us take a note that we have a minus or negative sign, and we have a decreasing function over this sub-interval. Now let us evaluate f prime of 4. This is equal to 3 times 4 squared minus 6 times 4 minus 9. The square of 4 is 16. 16 times 3 is 48. -6 times 4 is -24, then minus 9. When we simplify this, the final answer is +15. Again, we are more concerned on the sign of this number 15, and that represents the sign of the derivative on this sub-interval. Let us take a note here of plus sign, and we know that there is an increasing function over this interval. Now, step 5. Use first derivative test to determine whether the function f has a local maximum, a local minimum, or neither at each of the critical points. Our first critical point is -1. The left side of the -1, the derivative is positive and it is increasing, while the right side of this -1 is negative, that is decreasing. So we say that at x equals -1, the sign changes from positive to negative. Thus, there is a local maximum at x equals -1. Next, the other critical point is 3. Observing the sign of the derivative on the left and right of this critical point 3, we say that at x equals 3, the sign of the derivative changes from negative to positive. So we say that there is local minimum at x equals 3. Using GeoGebra, this is the graph of our function here. We can see on the graph that there is a local maximum at x equals -1. This is the point. Also, there is a local minimum at x equals 3. This is the point. This is now our final answer. I hope you learned something from this video. See you again next time.